Hello friends, now we are seeing an extended form of Coulomb's law in electrostatics. We already used Coulomb's law to find the force between the two charges or electric field produced by a point charges. Instead of a point charge or two charges, suppose we have a number of charge distributions. It is very difficult to use Coulomb's law to find electric field. In that time, we have an advanced form of this Coulomb's law known as Gauss's theorem in electrostatics. Actually, this Gauss's theorem is connecting the flux through any closed surface and a charge inside that closed surface. And mathematically, we will write that equation as the flux through any closed surface, or we can also write as electric field E dot ds through any closed surface is equal to 1 by epsilon 0 times the charge inside the surface. Actually, this is a mathematical relations between E area vector, the charge. If you want to find electric field, if these two quantities are known, we can find electric field. So this Gauss's theorem can use to find the electric field due to charges and charges distributions. See a simple situations, we are using this Gauss's theorem to find electric field due to a point charge. We already derived that equation by using Coulomb's law, and we have that equation E equal to 1 by 4 pi epsilon 0 q by r square. Again we are seeing or verifying by using Gauss's theorem. Suppose we are placing a positively charged particle, a point charge on the space. We have to find what is electric field at a point P, which is at a distance r from the point charge. We are using Gauss's theorem to find that. To apply Gauss's theorem, we need a Gaussian surface. It is nothing but an imaginary surface to apply Gauss's theorem. When you are imaging a Gaussian surfaces, the things to be remembered is that it should be a closed surface, or there should be some symmetry for the surface. Symmetry means either all the points on the surface are equidistant from the charge distribution, or angle between electric field and area element is known like that. So here by symmetry we are considering a spherical surface as a Gaussian surface. The advantage of this spherical surface is that all the points on the sphere are equidistant from the charge. That's it. So if you are taking a very small area element here ds, and we are taking a very small area element ds on the sphere, and we are showing its direction is radially outward or normally to the surface. This is the direction of area element. If you are drawing the electric field lines due to this charge, these are the electric field lines due to this point charge. That is, angle between the electric field vector and area element vector is 0. So if you are calculating what is the flux through this small area element, that's getting as the flux through this very small area element d phi is equal to E into ds into cos of angle between them. Angle between them is 0. So we are getting E ds into cos 0. See, since E is constant throughout the surface, as the all points are equidistant, E is symmetric, E is constant. So better, instead of finding the electric field due to all such a points, better you can integrating this one. The small flux can be integrated, that is total flux phi is equal to integral d phi, that is equal to integral that is equal to surface integral E into ds. Surface integral E into ds, that is the total flux. We are getting as total flux is equal to phi is equal to E is keeping outside E into what's integral ds. Integral ds is what? Total surface area. Total surface area is equal to what? Total surface area is equal to integral ds is equal to 4 pi r square This is a sphere of radius r. So total surface area is 4 pi r square. E into 4 pi r square. Okay. Now by Gauss's theorem, we know that by Gauss's theorem, okay, by Gauss's theorem, the flux is equal to what? Q by epsilon 0. That equate the flux with the Q by epsilon 0. We already calculated the flux. Flux is equal to what? E into 4 pi r square. E into 4 pi r square. And that's equal to 1 by epsilon 0 times the charge inside the surface. What is the charge inside the surface? We have only a single charge, that is Q. It's equal to Q by epsilon 0. That is E is equal to what? 1 by 4 pi epsilon 0 Q by r square. And see that electric field is inversely proportional to square of distance. That is, when the distance from the charge increases, electric field is decreases like this. Electric field is maximum, very close to the charge, and electric field is decreases with the increase of distance. It comes to 0 only at infinite. That's the electric field due to a point charge by using Gauss's theorem. Okay, thank you.